this is not good timing to have a makeup class, but however, there is no other break. I was intended to have this makeup tomorrow night, but I was asked but I was asked by the president to join a dinner with a lot of guests from East Europe, okay, Lithuania. Lithuania, they sent a group to our school to talk about the exchange program in the area of semiconductor. Okay, so we are going to have a dinner with them tomorrow night. So that is why I cannot have a makeup class in Thursday night. Instead, I have to give the makeup class tonight. Okay, we are going to have a break around 7:50. Is that right? Okay, 7:50. So you just sit back and relax. Okay, we talk about everything that we need to know at this moment about the sequential logic. As I said the last time and in the class, sequential logic is a core of a control or controller. So without the sequential logic, you cannot remember what happened before, and you don't know how to take the action for the next move. That is what the sequential circuit is. And this is the last slide I talk about, okay? We have to understand what the memory device is, okay, so that we can go ahead to design the entire sequential circuits. And this is the first type of memory devices. It is the simplest one. Okay, basically you can think that the G is a control. Okay, for that one without a circle, that is positive enable, positive or high level sensitive. When it is high, all the signal you see will be transmitted to the other side faithfully, literally. Okay, for example, the timing diagram, this one is dedicated for the top one over here. So as you see over here, that when the G goes high, so everything happen in data input D will be copied, okay, to the Q, which is the output, okay, faithfully. Okay, maybe a little bit of delay, but everything happen here will be totally copied at the output, okay? And that is one of the reasons I mentioned. The latch has a problem to reject the noise coupled in the signal source. Okay, that is why. And this is the simplest one. So this kind of a property, transparent property, how do we do that to reject the noise coupled in the source? Okay, basically you got to use the flip-flops. It's either the master-slave type or the edge trigger flip-flops. Or the last one is a pulse latch. Pulse latch is a behavior look like this one. Okay, it only worked. It only give a very short period of high signal, so that in this very short period, the most of noise will be deleted. So that is how the noise can be rejected from the transmission channel. That is how we do it. So we have three types over here, okay, to get rid of this problem. So we're going to introduce each one of them one after the other and another. So this is D-type. Okay, the D-type latch, which you can find in your freshman textbook, is very easy. It is based on the NOR, okay, a NOR latch. Okay, the NOR latch. So let's start from the very beginning. If you have a NOR, which, okay, if a NOR, you have two NORs. They are arranged this way, okay? So it's quite easy. That is how we draw it, okay? Okay, so you take a very quick look at it, okay? Perhaps you already know it, perhaps you forgot. Never mind, just go over it. Okay, this is called a set. And R stands for the reset. Okay, reset. And this is Q and the Q bar and the Q. So what happened here? If both of them, okay, if both of them are 0, let's assume this is the original condition. Okay, the original conditions, the initial state, this is what, I'm sorry, use a different color so that we can understand each other better. Or let me use a green one so that you can understand what is going on. Okay, let's assume the initial state of this latch This is 1 and this is 0. Okay? When both of them are 0. So this is 1, okay, 1 and 0. So the OR will become 1, the reverse comes 0. And 0 come over here, 0 and 0. The OR is 0 and the reverse is 1, so it's locked. Okay, well, so the answer is when set reset. Okay, so when there are 0, 0, Q will stay as a Q. Q next will be exactly as a Q. Okay, so when it is 0, 0, okay, whatever next will be the same as before. Okay, this is Q now, this is Q next. Okay, now let's change it a little bit. So what if we have a 1 and a 0? If we were to have a 1 and a 0 here, let's see what's going to happen. Okay, well, this is 0 and 1. Okay, when this is 1, what's going to happen? This is 1. I don't care what happened before. When this is 1, the OR will be 1, and the reverse will happen. So this one will become 0. And 0 come over here. 0 and 0 will become 1, become 0. This one will be, hold on a second. 0, 0 will be 0, and the reverse will be 1, yes. So when it is reset, okay, 0, 1, definitely Q is gonna get a 0. So this is reset. So when this is high, the Q will be reset. Okay, on the other way around, when you have a 1, 0, you're gonna get this one. Okay, you're gonna get this one. The only problem would happen is when both of them are high. When both of them are high, then one and the other one, I don't care what that is, definitely you are going to have a 0. And when you 1, I don't care what it is, you're going to have a 1 in reverse is 0. So you are going to have a Q bar equal to 0 equal to Q. Okay, technically speaking, it is okay. But according to the definition of complementary true, this is undefined. You cannot have a Q bar equal to Q. So what happens is this one are both high, you're going to have undefined. Okay, this is undefined. Definitely undefined. So the design over there is going to eliminate this scenario, so that in order to prevent this is going to happen, so what they do? Okay, they are going to use an AND gate over there. See that? Let's use an AND gate. Sorry. Use an AND gate. And the interesting part is that we are going to have a signal, which is called G. And this one is D, and this is D bar. D bar. Coming over here. So when you have a D, and this one is D bar. So because it's inverted, you are not going to have, because you use the inverter here, just like this one. So no way you are going to have these two conditions. So you just simply eliminate these two because of the inverter. Because you use the inverter, all right? So it's gone. So now so when D is high, this one will be low. Okay, or the other way around. When this is 0, they'll be high. Okay? So this is 1, 0, it will be this case. If it's 0, 1, that will be this case. So it's either set or reset. And what is a G for? G is called the enable signal. Okay? When enable equal to 0, then both of them are 0. Then this condition comes back. Okay? When enable is 0, that means S equal to R equal to 0. So next Q will be the same Q here. will be a thank you here. Okay? So G is going to provide the function that S and R are both 0. Okay? So that the state will be kept. Okay? Otherwise, D will be only two possibilities, 1 or 0. Either way is acceptable. And the beauty of this design is that we already delete this undefined case from this table. So this is why. So this is a very welcome and very simple latch that we widely use a lot of circuits, sequential circuits. Okay, and this is the symbol. Usually we don't draw so many gates. We use a box to stand for this latch. Okay, we use a box. And usually this kind of a latch or the flip-flop, we use a box with 4 terminals. Okay, SR, Q, and Q bar. And number 5, if there is any, it will become the control. It's either the control signal, enable signal, or the clock. Okay, this is a box. So stand for the latch. Okay, this is the latch. So the latch is there's a problem that D is so vulnerable to the noise. Okay, so how do we take advantage of this latch so that we can create a design to prevent the noise to go through entire the circuit? So we are going to take advantage of that one. Okay, so this is what we do. We use two boxes over here. Okay, they are all the same except one thing. Okay, they're all the same. Okay, now pay attention to this. The only difference of these two latches, two boxes, are the G over here. The G over here. Okay, so how do we do the connections? So this is still the D. This is still the D. Okay, D's come over here. And as for the D bar, I don't want to waste my time to draw it. As you understand that there is an inverter that goes through the R. It's the same over here, just like the one draw over here. I would like to have your attention for the important one is the enable pin, that is G over here. Okay, so check this out. And this one is called the clock. Okay, this one is called the clock. Now this is the fun part of this design. This design is a 2-stage design. This one is called the master, which is the first stage. This is D, of course. And you have a slave, which is the second stage. Okay? The only difference is that the master is enabled by the high of the clock. So this is the clock. This is the clock. So what's going to happen? Okay? Now, please follow me to understand this one, okay? So when clock is low, and the G over here, okay, according to the definition, when G is high, the entire box will go to the operation mode. When G is low, that means enable is activated so that the entire box is blocked. Okay, nothing will happen. So when clock is low, it's over here. Okay, when clock is low, this is high, this is low. Okay, whatever happened here will be copied according to the definition over there. What happened here, whatever signal here will be transmitted to output over here. So that's this part. So right now we are going from the high part. Okay, so let's assume we have a new data coming in. Okay, D coming in. D is not going to be copied over here until clock goes high. Okay, so when clock goes high, the D over here will be passed, copy over here. Okay, when it's high. And at the same time, okay, the second stage is 0. So what happened here will not be duplicated or transmitted to the final stage. Well, it will not, because this one is disabled. Only this one is enabled. So the new D is D new. It's copy, this is DO. Okay, it's copy over here and stay there for a while. Then all of them wait for the change of the clock. Then in the falling edge, when clock goes low, this one will go high. This one will go high. Okay, then this one, the first one, because it's 0, it's blocked. And what will happen? This D new, which was just copied from the original, will be transmitted to replace the D old. So the D old is gone. When it becomes D new. All right? Okay. All right. So this operation is considered as a sandbox. It is called a master-slave D flip-flop. And what at what moment the transition is finished? Okay, at what time? Okay, the entire operation is done. It only happened in this age. This is falling age. So from time to time, this kind of design, master-slave, okay, is also considered as an edge trigger flip-flop. Okay, so edge trigger flip-flop is equal to master-slave. Master-slave flip-flop. The only thing you have to be aware is that, is it the falling edge or the rising edge? Okay, this design is a falling edge. Okay? If I want to do the rising edge, how are we supposed to do that? It's easy. Okay? If you want to do the rising edge, you simply move this inverter, come over here. You move this inverter over here, it'll become the rising edge. Okay, that's it. No surprise. No surprise, nothing. There's no surprise. Okay, so this is the one that will realize a flip-flop, okay, to reject the noise. Because the transition, okay, for the signal to travel from the left hand, the original, to the destination only happen on the falling edge. And because it's a short period of time, okay, there's only small amount of noise will be transmitted, okay, from the source to the destination. That's all. So this is a D-type flip-flop. All right, and then okay, of course, there are other types. So we check the timing diagram over here. So this is a timing diagram. A lot of students will get confused or feel that feel dizzy because of this figure. Okay, we gotta understand what this timing is called a timing diagram. What does that mean? Okay. Now please pay attention to on the screen. So if you are going to use a flip-flop, please watch this. This is flip-flop, and this is a latch. Flip-flop only pay attention to the edges. It could be a rising edge, it could be the falling edge. So this is what happened over here. Okay, this is the data. Okay, data could be changed at any time. It could be any signal, high or low. We don't care. But here, this is a rising edge. Okay, so when this is going up, we do the sampling at D. So here we find out. Okay, here this is a sampling edge, the rising edge. So this one that we sample, okay, find out this is 0. So the flip-flop will go slow after a while. Okay, and then nothing changed. Even though a lot of changes over here, we don't care no more. Okay, until the next rising edge. And we check again. It goes high, then the output of flip-flop goes high. Okay, so the flip-flop, you only pay attention to the edges. Okay, edges of a clock, that's all. Okay, now there are two important parameters because we are going to deal with them for the rest of this class. Okay, for the data to be correctly sampled by flip-flop, we got to make sure the data is well prepared before a moment, before a period of time. And the period of time before this, the edge here is called the setup, time setup. That means that the data must be stabilized, D must be stabilized before T setup. And T setup is the time from the center of the rising edge over here. So if the data is not ready, because the data is bouncing, then there is no guarantee that the data can be correctly sampled by the flip-flop. So this is called a setup time. And then the data is asked to be stabilized after a while, okay, after the sampling edge. And the period of this time is called the T hold. So it's a setup time the whole time. So the data, okay, let me repeat again, it's quite easy. The data must be stabilized before and after the edge that you are interested. Okay, before the edge, it is called a setup time. And after the edge, it's called the hold time. So you got to make sure that data, D, must be stand there, no move, don't move. Okay, if it is bouncing in this period, in this duration, then you don't know what you are sampling. Okay, it's the same over here. So you got to satisfy the data must be stable before T setup and stable after T hold. All right, and on the other way around, if you are using the latch device, okay, what we are looking at is not the rising edge, okay. What you should pay attention is the falling edge, because the reason is, okay, the latch allows all the data to be changed during clock equal to high. So it can bounce, coming up and down, whatever you like. The only thing we care is, okay, when the clock or the enable signal goes down, so to close the latch, okay, we have to make sure that the signal is correctly simple. So again, we have to make sure that data is ready or stable before the T setup, and stabilized after the T hold, just like what happened on the other side of a clock duty cycle. Okay, so this is important. And all these blue curves, they stand for the sequence of the events. So this thing must happen, then this will happen, and this will happen. And again here, the edge is here, okay, this one comes over here to make sure it's right, and it is stabilized over here. So no matter which device you use, flip-flop or latch, no matter which one you use, you got to satisfy, or you got to make sure the data, D, must be stabilized before T setup and after T hold. That's a requirement. Otherwise, you don't know what you are sampling. Okay? This is a timing diagram. And we are going to deal with a lot of timing diagram in this lecture. A lot of students get confused. But don't worry, it's not that hard. Okay, so we are going to make a short summary about the comparison of latches versus flip-flops. So latches, okay, we have control gate latch, just like the one we draw on the board. And the other type is multiplexer-based latch. Okay, we're going to see it very soon. But my experience that multiplexer latch is not that welcome, okay, because it has too much problem, because you need a control line, this kind of thing, make a lot of connections. And for the design with flip-flops, okay, a lot of students like to use this one, master-slave. Okay, the master-slave, the only problem is that, okay, ideally, the clock on before and after the inverter shall be perfectly divided. But in fact, it is not, okay? There is a short period of time, okay, the rising edge and the falling edge on both sides will be overlaid a little bit. Okay, that is what we are afraid of. So there is a very short limit of time and a very a teeny tiny possibility the D will be directly coupled to the D out. Okay, that is what we are worried about. So the edge trigger flip-flop, which you can find in the textbook of the freshman course, which is called the digital system design, there is another different design. The edge trigger flip-flop could be composed of 4 pairs of NAND gates. Okay, 4 pairs of NAND gates. I don't see that in my PowerPoint file today. Okay, but you still can go back to your freshman course and check it out. Okay, and the last one is very much welcome in industry. It's called a pulse latch. Okay, pulse latch means that we only open the window a short period of time so that we can finish the data transmission, then we close it. That'll save a lot of power. Okay, save a lot of power. I myself had this kind of project before. Okay. Okay, so let's go to see the circuit design so that you understand how to do the design over here. So this is a one, okay, without the NAND gate, without the AND gate. So you take a look, see that we have 2 NORs. So where are they? 1, 2, 3, 4. This is 1 NOR. 1, 2, 3, 4. Another NOR. Okay, so how many transistors we need? 8 transistors. And this is the inverter that is over here, the same. So this design is a simplest design for students to follow. 10 transistors, that's all. And if you like to add these 2, that's another 1, 2, 3, 4, 5, 6. No, 1, 2, 3, 4, 5, 6. That's another 12. So a total of a complete design will be around 24 transistors. So this is a D-type latch, very easy to follow. Okay, 2 NOR gates, just like the one we see. And the size can be tuned by the way that we talked before. All right, and this is the control, okay, which is enable. What is the difference over here? Check this out. This is an extra transistor, okay, over here. This is a foot switch over here. When E equal to 1, okay, when E equal to 1, that means the first switch is on. So the D function over here, the NOR gate here and there, will be normally operated. But when E is 0, the first switch is closed. So the NOR function is killed. That's it. So this is the enable pin to enable the entire operation to function, okay? And this one could be considered the function just at least 1. But the thing is, you only add 1, 2, 3, 4 transistors, you can get it done. Here, if only add this function, you need 6 transistors here. No, not 6 transistors. 1, 2, 3, yeah, 6. 6 and 6. You need 12 transistors, okay? Because it's an NAND gate and an inverter. That's an N. That's 6 transistors. 1, 2, 3, 4, 5, 6. Yes. You need 6 on top, 6 in the bottom. Here you need 4 transistors. Okay. It's much more cost effective. Okay. This is control gate latch, and it is very much welcome. Now let's go to see the multiplexer MUX-based latch. Okay. This is a one. MUX-based latch. Okay, we have 2 types. Let's check the first one. The first one can be simplified as this way. The first one at the top. Okay, this is the control, COK. Basically consider this way. Of course, that's a transmission gate. And when clock is 1, the data will be passed over here, okay? And what is this? This is a loop. This is a loop. So as soon as you see a loop, you know this is a device to remember what happened before. So this is the idea how to do that, okay? Okay, the simplest way to use a switch, okay, controlled by clock. Then you have a loop, okay, after the transmission gate or after the pass transistors. That's it. And basically, this is a big one. This is a big one. This is a small one. The difference between big and small is the ratio of W over L. Okay, because the one in the bottom is a forward pass. It's a forward pass. Basically, you like to transmission the signal straightforward to the output. And on the top is a feedback. The feedback, you cannot make it too large to compete with the forward pass. So basically, you got to have a small one. So you either increase the width of the big one, or you increase the length of the top one. Okay, either way is acceptable. Okay, either way you have to pay the price of area, that's all. Okay, so this is WL ratio here. WL big, and this is WL small. Okay, it's up to you which one you like. You either have a very fat forward pass inverter, or you have a very slim, thin feedback inverter. That's all. And for the second one, it's very interesting. It is called the MUX-based latch. Okay, I use the left one as example over here. You have a 0 and a 1, okay? And this is D. And you have a buffer. Okay, this is a buffer. And it's one coming back over here. And this is clock. It's quite easy, no problem at all. You see, no matter which case you use, you always have a loop. Okay? This one, you also have a loop. See that? This is a loop. It's also a loop. So no matter which memory element you select, there's a loop. You cannot get away from that. Okay, so it's quite easy. When clock equal to 0, then 0 we select a Q over here. So Q, whatever it is, Q will come in over here because we select the 0. It will come back again. So the Q next will be the exact Q now. Okay, exactly the same. All right. So the difference is that when we select, when the clock goes too high, we no longer select the original Q. We are going to select the D over here to go over this buffer and replace the original Q. So the 0 and the 1, 0 will go through the loop to refresh it. You select the 1, you are going to select a new input to replace the old one. Okay, this is a MUX-based. Okay, MUX-based. Okay, you can use to select the 0 or the loop going back from the 1 pin, that's fine. Okay, it's up to you. It's up to you. Okay, this is MUX-based latch design. Okay, now these are a little bit more complicated, the MUX-based MUX-based latch. So I'm going to use this one to let you know how it works. Okay, because we're going to show it quickly. I'll do it over here. So let's check the left one. Okay, I'm going to use this way to represent it. Okay, and this is D, and this is Q bar. Okay, if letter Q, that's fine. Okay, the important thing is that the control of these two switches, they are out of phase. The first one is COK, and the second one is a COK bar. Okay, COK bar. And what does this mean? Okay, let's check. Okay. The first one is controlled by COK, and the second one is controlled by COK bar. So when the first one is 1, okay, when COK is high, what you see? When COK is high, this one is short circuit is on. So the D will go over here and become the D bar. Become the D bar. D bar will become the Q bar. It's the same because we have an inverter. So they are the same. Okay, all you need is add an extra inverter to invert that to be the D again. So this is the 1. So when clock is high, this is on and this is off. Okay, this is off because it killed the top one. Okay, so the loop is disconnected. Now, when the clock drops to 0, then you don't see anything here because our clock is 0. This one is off. Okay, but the loop here is on. So whatever you have will be refreshed again. So the Q bar will be the Q bar again. So this is a refresh. This will be refresh. So clock equal to 1, we update the Q. Okay, when clock is 0, we refresh the Q. Okay, this is a single stage multiplexer based latch. Okay, this is a single stage. And you see this is a variety of this one. See, we add another inverter, so the D bar, the Q bar will become Q. And this one is a copy over here, will become the Q bar. That's fine. Okay, anyway, the important thing is about the control, not just a signal inversion. Okay, that is what you get. All right, so, and next thing I want to tell you is that, okay, we can duplicate and reverse the clock to have a similar function like the master-slave latch. See, right now I copy the circuits. Okay, I copy the circuits. Okay, I copy the circuits, and it should become this way. Okay, now this is going to be lovely. Watch out. This one is controlled by clock. This is clock bar. If you now cascaded these two stages together, okay, make it short circuit together. This one is controlled by COK bar. And this one is controlled by COK. That they are the same phase. Okay, they are the same phase. Okay, why do we do that? Okay, see, now when the clock is 1, this one is on, this is off. So the new data is coming over here. Okay, stay there, but this one is 0, so it's off. Okay, disconnected. And this one is doing the loop and the refresh. Okay, that's when the clock is 1. Right now, let's change the clock to low. Change to low, this one is disconnected. This one is on. It's looping. And the new data, because this one is become 0, the inverse is high, right? So the data we just copy will be copied again to over here. All right, and this one is disconnected. So if we copy the two to design, but driven by out-of-phase clock, we are going to have the exactly same function just like the one over there, master slave. Okay? And the beauty is that how many transistors we need over there? Check this out. Okay, you need, this is 4 transistors, and this is 6, right? 10, and then this one will become 24. Okay, you need a 24 transistor for the single box over here. And you have 24. And this is a 1 over here. Okay, how many we need? You have another 4, and another 2. So we are going to have a total of 50 transistors for this design. How many we need over there? Check this out. Okay, how many we need? This is a transmission gate. We need 2. Okay, inverter. Another 2. So for each stage over here, we need 1, 2, 3, 4. We need 8. We need another 8 transistors over here. So a total of what? 16 transistors. A more economic design to carry out the same function. This is why a lot of students like to use this one. Okay? Very, very efficiency design. Of course, you got to spend some time to tune the size properly. Basically, the forward pass, okay, will be stronger than the loop feedback pass. Okay, this is how we make sure that there is no competition at any node. Is that understood? Okay, very simple. Okay, no special. Okay, so the differences between these two ones, they are both called master-slave design. Okay, this one you need 50 transistors. That one you only need one third of the transistor numbers over here, which is 16. Okay. All right, and this is a standard figure for the flip-flops, DT types. Because it is edge trigger, so I have to highlight, show you that there is a triangle over there to tell the reader this is the edge trigger. It is not a level sensitive. So if there is no circle, that means it is positive edge trigger. And this is a state diagram that you already, I suppose you know this one because you took the course when you were a freshman. Okay, and this is a Moore machine. Why is Moore machine? Moore machine that say that the definition of Moore machine told us that the output, okay, is only generated by the state, not the input. Okay, so the difference of the, okay, I got it. Let me erase all of this. Okay, I'll show you the difference. I'll show the difference between the mini machine and normal machine state diagram. Okay. Okay, if you see a state diagram like this one, for example, I use the D flip-flop as the same, okay? And you have a state 0 and state 1. You have a state. And then the input, when the input is 1, okay, when the input is 1, this is the input, and there's a state output. This is called the output. The output. So when you see the operation like this one, and there's when this is 0, output is 0. Okay, input, output, and this is the state. Okay, and here we gotta have a capacitor come back. If you see a state diagram, and the arc, or the curves are labeled with something on one side of a slash line and something on the other side of a slash line. This is the mini type of machine. This is mini type, mini machine, because the output, this is the output, where the output is. Okay, output is correlated to the state and the input. This is the definition of mini machine. By contrast, on the other way around, you can look at that. Okay, that is another state diagram. You also have two states, but the state 1, state 0 will generate the 0, state will give you an output 1. Okay, and then you have a D coming over here, and D goes back when it is 0. D equal to 0, nothing changed. D equal to 1 stays there. See? And this is more machine. This is more. Why? Because the output is here. This is where the output is. Okay? So you check where the output is, then you find out which machine you are talking about. So this is the characteristic table. If it's 0, the next state is 0. Perfect. Okay? So this is a state excitation table. 0, 0. Okay, then D equals to 0. 0, 1 when it is 1. 1, 0 when it is 0. 1, 1 when it is 1. So this is also known as excitation table. It's the type of flip-flops. Okay, so this one is the Moore machine representation. Okay, of course you can represent it with the mini machine style. Okay, and this is one I just showed you, exactly the same. Okay, the only difference I use a simple way to represent it. You see that? This is the first stage, master D-latch. Okay, this one is controlled by the clock. This is clock 0, clock bar, sorry. And this is driven by the clock. And this one, okay, is driven by this one. And this is driven by this one. So in each block, the control of the transmission gates are out of phase. They are totally opposite. Okay, totally opposite. But this one is controlled by clock, and this is by clock bar over there. Okay, it's coming over here, clock bar, it's driven by over here. So this is the one exactly the same as the one I draw over there. Okay, the first stage and the second stage exactly the same. The only difference is that the transmission gate of the first one is controlled by one phase of the clock, and the other one is driven by the other phase of the clock. This is D-type flip-flops. Okay, I think my figure is more neat for you to understand. All right? Well, that's quite cool, huh? Okay, and this is how the operation is. Okay, it's the same. See, I use this. I use the arrowhead, and the textbook uses the arrowhead as well. Okay, when clock is 0, this is on. Okay, another one is off, and the second stage is reversed. So the data will be written, okay, into the node in the middle. Okay. And the old data will be refreshed by itself, okay? And when the clock phase is changed, okay, the first one will be off, and the sample data will be refreshed by itself, and then in the meantime, it is copied to the output. A copy to the output. It's the same operation I just talked about. It's called a D-type D flip-flops. It's quite easy, okay? Nothing special, okay? Just go home and draw the figure by yourself and do some practice. You understand how the operation is, okay? No magic at all. Okay, now let's go to the next one. It's a little bit more complicated, but not that hard. Okay, what is this about? Because there's a function I forgot to bring to your attention. Okay, when we check almost all kinds of flip-flops, they must at least have one of the functions. It's called a reset or preset. Okay, the clear is the same. Clear means the reset. That means Q becomes 0. Q becomes 0. Okay, the preset means that if it is activated, that Q equal to 1. It depends on which one you like. At least you got to select either one of them. Okay, one of them. Okay, you might not have both, but you got to have one of them. Okay, because when the system is powered up, you don't know, okay, the original state after the power up of the flip-flops. You got to make sure that all the flip-flops, okay, will be entered to a predefined state after you turn it on. So we got to remember this one. All the registers, okay, flip-flops, latch, okay, memory. These devices, after it's power on, okay, when it is power on, they got to go to initial state. We don't care what that is, okay? You can give it a 0, give it a fine, as 1, that's fine. Remember your system. When you turn on, power on your cellular phone, you power on your PC or notebook, okay, it will enter a predefined state after a while, okay? That is called power on self-test, and everything is good. Okay, you can start to use the machine and enjoy the game that you want to play, okay? So after power is on, everything with memory features must enter so-called the state. So here the flip-flop is the same, okay? Okay, the clear or the reset means that you got to be 0. If it's a preset, that means it is written to 1. Okay? Either way is acceptable. Make up your mind. Most of the cases, we like to use a reset or clear because it's easier to be understood. Okay, I like to clear everything before I enter into certain operation mode. Okay, so most of the cases, we like to use this one. Okay, of course, in some design, they prefer the preset. That's fine. Okay, it's the same, just a little bit different. That's all. So let's check out how do we carry out this function. It's quite easy. All we need is to add a few gates. Okay, watch out. Okay, all the designs are the same, except 2 things. In the forward pass of the second stage, okay, the original one is an inverter. Is that right? Okay. And in the first stage, the feedback cast is an inverter. Both of them are replaced with a NAND gate, two input NAND. So what is this about? Okay, let's check over here. Okay, this is one of the input. Right now, let's assume that it is 0. When this is 0, okay, when this is 0, what's going to happen? When this is 0, I don't care what that is. Okay, I don't care what the other one is. Okay, when this is 0, and you will see what 0 will become 0, and it will become 1, right? So Q will be automatically set to 1. So when this is 0, we carry out a function called a preset, because preset function is defined as we want the output to be 1. That's it. Okay? It's quite easy. Okay? No one gets hurt. Okay? It's the same over here. So when this is 0, and the inverter here will become 1. Okay, it will become 1. So the contents of this flip-flop will be automatically written in 1, sorry. Will become 1. So this is all you have to change. Okay, replace these 2 inverters with 2 input NAND. And one of the inputs is shorted to the preset, and that will do it. This is called a synchronous settable design. Okay, now this is a latch element. All right, this is a latch element. This is TG-based dynamic latch, different kind of design. But this kind of design is kind of risky. What do I mean risky? Okay, now check this out. This is the previous design. We use a loop, okay, to memorize what happened before, what the status, okay? So this is a loop. Loop is a memory device. And then a lot of people say, okay, why don't we just use a capacitor to remember what happened before? Because capacitor is also the memory device that can remember the state, okay, of the previous one. So some people say, why don't we use just a CX over here? And the strategy to create a big CX is that we have a very big inverter, okay, or we have a capacitor over here. So if this is the case, all we need is a switch over here, a memory device, and an inverter. That's all. Okay, this is called dynamic. Then when clock is on, Vin will be coupled to X, and it is inverted immediately to become VL. So anything looks like this one. Anything with a clock-controlled switch to carry out a memory-like function is called the TG-based dynamic latch. As I said, it's kind of risky. Why? Because you got to remember this. All the capacitor is not perfect. It's not. Because it is realized, fabricated using semiconductor materials. There is a risk to have a leakage. When there is a leakage, the voltage here will go down very fast, so that the original high signal will become low after a while. If you don't take any action, then the logic value here will be changed from high to low. If you want to keep it longer, you got to have a very big, fat capacitor here, okay, to keep it longer. That is a price you have to pay, and that we don't like, all right? So you got to have you either have a very high-speed operation, or you got to have a very big, fat capacitor to help you. All right, anyway, this is just a design. And as I said, a lot of a design has been published or publicized in articles, okay, and all of them claim to function just fine. Well, personally, I am not sure that what they say was correct, because I have been always an IT designer for a while, and I ask my students to realize everything on the silicon and the measurement, and do the measurement to make sure to validate that their design idea is good. Well, and a lot of papers, they are published just based on the simulation results, and that is something that cannot be convinced. Anyway, so it's in a textbook, so I have to give it, show you how it works. All right, so this is a design. And this is a design similar to this one, but slightly different, okay? So the VIN this is like the one that we introduced, is the C square, clock CMOS. So when the clock is low, this is off. This is off as well. So the V in, whatever that is, will be blocked. Nothing will be changed. Okay? So when clock is low, this one is locked. No one changed. Okay? Just like the one over here. So we have 2 transistors. We have another 2. And then the inverter here is split into 2 parts, just like this one. So when the clock is high, this one is low. So both of them are on. Then the V in will be inverted by the inverter over here to become the V out. So basically, these 2 functions are the same. They have the same functions, okay? And this is called the clock inverter. But this one cannot be, it cannot swap both of them. Why? Because the problem is, first of all, when this is high, we have a charge sharing problem over here. Okay? Secondly, when this one is suddenly high, we have a risk to pull down the V in. So basically, because of the charge sharing, okay, the charge sharing over here, when the size of these two capacitors are almost the same. Remember we do this analysis before. If you want to keep the voltage here close to high, you gotta make sure that the size of CX is 10 times larger than this one. Remember the charge sharing equation we derived last time? Okay, at least 10 times. Okay, otherwise you cannot take the risk. The charge on the top of CX will be shared by the CB over there. Okay, so that's one. That is the major reason why we don't like this kind of design. But the middle one is okay. There is no risk to suffer from the charge sharing. All right, okay, so this is one. And then let's move on to see the interesting one. Okay, now this is a clocked CMOS dynamic latch. Okay, the area is much smaller than the TG based. Okay, this is one over there. They think they want to save more areas, and this is one. But again, I don't believe it worked just fine because a lot of my students fail in this design. All right, and these are 2 types. Okay, this is clock bar, and this is opposite clock bar and the clock. Okay, so that it is understood they are out of phase. They are out of phase. Of course, they can be cascaded together to become a latch. No problem at all. No problem at all. Okay? But you gotta be aware that when the clock goes up and clock goes down, there is a limited window, very small window, both of them will be turned on. Then there's a risk that we have a short circuit, which might destroy the data. Okay, so these are the theoretically fine circuits. Okay, now researchers couple them together. Now this is called a TSPC. Okay, how it works. Okay, check this out. It's fun. This is clock, right? Okay, this one is driven by clock. Because the previous one, we need clock and a clock bar. Now let's check this out. Okay, let me show you why TSPC is so welcome. You check this out, you're gonna love it. Okay, because this one is driven by sorry. Okay, now the problem is these two. Okay, remember that we always say this is clock, and clock power shall be perfectly aligned with the clock bar. But the thing is, most of the cases, COK go this way, double buffered, then we take another one. This is COK, this is COK bar. Okay, most of the cases we do this way. Now this gives us another risk. That is the slope over here, they are not that straight. Okay, from time to time, they are slanted. So is the clock bar. So there is a risk. There is just a little bit of risk that both of the transistors will be on. That is what we are worried about. If you connected two stages together, you might have a risk that in this period of the time, both of the transistors are on. Then you might kill the data. Okay, you might kill the data. So this is why it's kind of risk. Then the people who invented the TSPC say, we don't want clock bar. They simply take this one away. Then if we take this one away, that means we don't need this no more. Then there is no risk to turn on both of the transistors in the pull down, pull up and pull down pass. So this is why the TSPC is so welcome. See that? We only need either single clock in this side, or we can use a single clock on that side. If your control is NMOS based, we use clock. If it's PMOS, we use a clock, another clock, that's fine. So when clock is low, this one is blocked. Nothing will happen. Okay, there's no change. You cannot pull it down. But when clock is high, V in will be inverted again. Okay, just like what over there. That's driven by clock bar. So it is called a TSPC. TSPC means true single phase clocking. Only one clock is needed. Okay, we don't want the risk to have that kind of jeopardy. We don't want to jeopardize the circuit design. Okay, because there we cannot control the overlapping of clock and clock bar. All right, is that understood? Okay, so this is very much welcome in a lot of design. And some of my students really carry out the circuits just like this one. See? This is one that we talk about. Okay, when clock is 1, it's transparent mode. D will come over here, be sampled, and driven again by Q. Okay? And when clock is 0, this one is off. This one is off. So whatever happened before will be kept at the node over here. So nothing will be changed. So there is a sample mode, or AKA transparent mode, or okay, when clock is low, it becomes a hold mode. The data is supposed to be kept, okay, maintained there for a while. And this is the TSPC dynamic latches. It is very much welcome. Okay, a lot of people use it, including my students. So before we take a break, I just let you know, since there are only 5 students here, I'd like to give you a good news. Today, the MOE of Taiwan government, Ministry of Education, just announced that our school, and that's why SU just got granted for 5 years, each year, over 400 million NT dollars. Okay, you can check the news out. It is termed as 高教生根计划. It was announced today. So we are right behind the top 4 universities in Taiwan. Well, even though the overall amount that we have is slightly lower than Central University and the Zhongxin University, but if you divide the number of students and the faculties, that we are number 5 in the entire country. I'm not sure whether you will be proud of it or not, but I myself, I was in charge of these affairs. I feel a little bit comfortable because, you know, this is a lot of pressure on me and my team. And in the last 5 years, okay, our school was granted about 300 million, a little bit more, about 300 million. And for the next 5 years, we are going to receive over a little bit more than 400 million. That is a very significant jump in terms of money. And the growth rate will be around 20 to 35%. Okay, that's quite an achievement. But it seems to me that your president was not so happy about it, okay, because the top 4 universities in Taiwan, any one of them got 1 billion. 1 billion. Okay, our school got 4-something million, and the top 4 university, they got around this one. Around this one. It's about 1 billion. 1 billion. Okay, and well, but if you check the size, I mean the size of these universities, we are the smallest one. The number of students of NSYSU less than 10,000 students. And the number of faculties, the professors in our school is less than 600. And do you know how many faculties they have in Cheung Kong University? Over 2,000. 3 times of our school. And for the NTU in Taipei, they are over 3,000 faculties, professors. So the size is different. And if you check the number of students, okay, the number of students in NTU is 3 times more than our school. So quite naturally, all the higher education resources will be invested on these top 4 universities. It's because of the size. And well, there's nothing we can argue about it. Okay. Well, the pity thing is that no matter you like it or not, this school is still the number 1 in Kaohsiung City. I don't think this is quite right to give us this kind of money. I think we deserve a little bit more. In fact, I was the one to escort our president to do the report and presentation to the faculty of MOE. And we kept emphasizing that we are the locomotive of everything in this city, but it seems that they don't appreciate this idea. That's too bad. Anyway, I did my best, okay, and hopefully that all the professors and the students will fully utilize the money that we just received, okay, in the next 5 years. Well, I'll be retired in the next 5 years, and for the next term, it's not my business. I have done my job, so it's better for you to pray you have a better, vice president to carry this out. Okay, just to let you know. All right. And this is operation. Sorry, I forgot this one. Okay, before we take a break, this is operation. See that? This is how it works. Okay, so you have the circuit like this one. You cascade them together. So the first one is driven by clock bar, and the second one is driven by clock. Then when clock is low, okay, V in is copied to X, okay, and inverted over here. But because this one is open, okay, nothing will be transferred from X to Y. And in the next phase of the clock, okay, this one is off, then this one is closed and turned on. X will be inverted and transferred to Y, and then inverted again. Inverted again. So the V in will be logically equal to V out, okay, for this operation. But this operation, as I said, there's a risk, okay, because these capacitors, they have a problem of leakage. You want to do this transfer, fine. You got to do it very fast before the Vx and the Vy drops below the threshold voltage. If they are dropped below the threshold voltage, it will become unknown. Then the operation is totally contaminated, and you don't know what you are receiving at the output side. Okay, that's pathetic. Okay, that's pathetic. Okay, and okay, here we go. This is the failure. Why it will fail? This is why. See, I forgot that we have a better picture to show you this one. See that? As I said, we have a risk like this one. This is clock, this is clock bar. And because you use the auto phase, and there is a risk for both of these transistors, both of these switches are short-circuited and on, then you might kill the Vx over there, the overlap. Okay, this is an overlap problem. So from time to time, all of this kind of timing control, I always, my students, one question: how the hell you can ensure that your clock sources are synchronized and then non-overlapped? Okay, it's very hard to answer that. They always say they have a function generator to do that. I say, never trust those machines. Okay, because why? Because those machines are coupled with a lot of noise, and the power supply was given by the power LED on the wall. It's not stable at all. It's not stable at all. So this is the reason why I always ask them, if you want to do that, that's fine. Please generate all the clocks internally, and you got to add another testing circuit to make sure that all the clocks are generated correctly. Okay, tears are here. So we take a break. Let me get a cup of coffee. I'll be back.